Diffusion models are a significant milestone in generative modeling, achieving state-of-the-art performance and beating GANs without the difficulties of adversarial training. They work by reversing a stochastic noising process, generating samples from pure noise using a trained neural network. As such, they can recover structure in the data and generate our data distribution from a pure noise-based distribution. In our video on DDPMs, we saw how these models could be trained using variational inference, and how this objective is equivalent to the objective of noise prediction on the corrupted images. In this video, we'll explore how there is in fact a third mathematically equivalent interpretation, and that is through the lens of score matching. This interpretation gives us greater insight into exactly why diffusion models work, and enables us to transition smoothly to continuous time diffusion in later videos. So in this video, we'll explore what exactly score matching is, how it can be used for generative modeling, and how it links to our DDPM loss. This is the second video in a 9-part video series on diffusion models, exploring their mathematical foundations and practical implementations. In the first video, we explored the theoretical basis for these models and derived the simplified noise prediction loss of the DDPM, so I highly recommend checking out that video if you haven't done so already. So, without further ado, let's jump in. Now, to understand score matching, we first need to understand the goals of generative modeling more broadly. Put simply, generative modeling enables us to learn distributions of samples in some n-dimensional data space represented by X. So, we imagine there is some true data distribution that we want to capture, P star, and this would be represented by our dataset. Now we can model this true distribution by defining a model distribution with parameters theta, then optimizing theta such that the two distributions align as closely as possible. In other words, we want to find some theta such that high probability regions in our model distribution match regions where data is common in our dataset. Since we're maximizing the likelihood of real data samples under our model, we call this strategy maximum likelihood estimation. However, there's one major difficulty in using a neural network to model a probability distribution, and it's that probability distributions are normalized, meaning that their integral over the entire data space is equal to 1. This means that we would have to divide our neural network output by this integral, which becomes a normalization constant z. The trouble is that if f is a complex function, as is typically the case, then this integral is intractable. We have no closed-form solution, and if x is high-dimensional, then it's also infeasible to estimate the integral numerically. But fortunately, there are a few ways of dealing with this problem. In the last video, we explored the approach of variational inference, where we created some latent variables, x1 to big T, then optimized our latent to data mapping to maximize a lower bound on the log likelihood. In this video, we'll take a different approach. First, we take our normalization equation and log both sides. Then we take the gradient with respect to the data vector x. Now, since the normalization constant z is invariant with respect to x, this term just reduces to 0, and we find that the log gradient of the likelihood is in fact equal to the log gradient of the neural network output. This is excellent because computing the log gradient of f is often feasible, and it gives us a way of knowing the log gradient of p as well. Now, this gradient of a log probability with respect to x is very important, so it has a special name, which is the Stein score, or just score for short. Now, for any statisticians out there, keep in mind that this is different from the typical usage of the word score in statistics, which denotes the log gradient with respect to the parameters rather than the data. Now, how does the score help us with generative modeling? Well, it turns out that if we align the score functions of p star and p theta everywhere, then the underlying probability distributions will also be equal to one another. The intuition is straightforward. If the log gradients are equal to one another, then log p will follow the same landscape topology for both distributions. The only way for the log densities to be different in this case is for them to differ by a constant k, which translates to a coefficient for the densities. However, if we integrate both sides and set both integrals to 1, then we find that e to the k must be 1, therefore the densities are equal. And so matching the score is equivalent to matching the actual densities. Now this means that we can actually frame our generative modeling problem as a regression task on the score, penalizing the Euclidean distance between the true score and a score predictor neural network. Now we're actually going to slap a 1/2 coefficient in our score matching loss, and this is just for mathematical convenience when we take derivatives. As it turns out, this expression is equal to a quantity called the Fisher divergence. So score matching is equivalent to minimizing the Fisher divergence from p star to p theta, while variational inference minimizes the Kullback-Leibler divergence. So now what we've discovered is the idea of using score matching to train generative models. If only we could match the scores, then we'll match our densities as well. So in this video, we'll see how we can train what are called score-based generative models. And here I'm following the framework set out by Song and Ehrman in 2019. But to understand how they work, we first have to sort out two basic components. The first is score matching. How do we actually train our score network? And the second is sampling. Assuming we have a perfectly trained score network, how do we actually use this to sample from the distribution? So first, we'll see how we can equate score matching to training a denoising autoencoder. Then we'll see how we can use Langevin dynamics to generate samples from our learned distribution. And finally, we'll connect this all back to diffusion models and show how score matching is equivalent to noise matching in the DDPM. So to train our score network, we need to deal with two problems. First of all, we lack direct access to the score of p star because p star itself is unknown. This means that we lack a training target. Second, because this loss is an expectation over p star, we'll draw very few samples from low density regions of the data space during training. So supervision will be weak in these regions, and our score predictions could prove to be inaccurate. This is especially problematic for low density regions that lie in between data modes. So we need to find a score target, and we need to deal with what we can call the coverage problem. Now, for the first issue, there are actually a few ways to get around having to calculate the data score directly, and one of them draws a clever connection with denoising autoencoders. To understand denoising autoencoders, let's first clarify what a standard autoencoder does. The autoencoder is a neural network architecture that consists of two main components. The encoder compresses data into some latent representation, and the decoder projects it back to data space. An autoencoder R is trained to reconstruct its own input through this latent bottleneck. One possible benefit of this compression objective is that the model will learn some meaningful features that capture structure in the data. However, with sufficient capacity, it is also possible that the autoencoder just learns a trivial identity mapping, essentially copying over the input rather than distilling it and reconstructing it through a meaningful, compact representation. In this case, the model doesn't really learn the underlying structure in the data. One solution to this is to train the autoencoder not to reconstruct x given x, but to reconstruct x given a perturbed version of x with Gaussian noise introduced, which we call x tilde. Now, the model can't just learn an identity mapping, it must learn some structure in the data to infer what clean sample must have given rise to this noisy sample. This is now called a denoising autoencoder. But how does all this tie into score matching? Well, consider for a moment that we use a Gaussian as our perturbation, with standard deviation sigma. If we apply this perturbation on p star, then we'll get a smoothed version of it, which we call p star sigma. Now, it turns out that learning to reverse this Gaussian perturbation is equivalent to predicting the score of the perturbed data distribution. To see why, imagine that we have a single data point at point x. Now, with sigma equals 0, we can imagine this as a Dirac delta function, which is 0 everywhere but x. Now, with some non-zero positive sigma, this function spreads out. and no matter what the value of sigma, two things remain the same. First of all, the mode is at x, and second, the score of the conditional distribution always points toward x. This is because the score of p sigma is parallel to the gradient, and the gradient always points toward the mode, which is at x. Now, a denoising autoencoder learns to take some sample from p sigma and map it back to x, which is equivalent to climbing the gradient of p sigma. Therefore, the denoising function transports the input in the same direction as the score. Now, we can be more precise about this by actually deriving the score of the Gaussian, and here we find that it points straight from the noisy sample to the clean sample. So any model that has learned to predict the score of p sigma can perform denoising and vice versa. This is the mathematical argument for why denoising and score matching are equivalent objectives in the case of Gaussian corruption. Therefore, we can draw an equivalence between the denoising loss and a score matching loss, averaged over x and x tilde, where the target is the score of the perturbed conditional. We call this our denoising score matching loss. Now, it turns out we can prove that this loss is equivalent to score matching on the marginal perturbed distribution p star sigma, which is a mixture of Gaussians where each mode is a real data sample. This equivalence is very useful, because the marginal is just a corrupted version of p star itself, which we want to find. To prove this, we just have to work through some algebra, and I'll go through this very quickly. It'll barely take a minute. So the first thing we do is expand the square difference. Then we realize the third term here is constant with respect to theta, so we can ignore it. Now we can split the expectations, are expressing our second term as an integral. And let's focus on that integral for a bit. So here we can differentiate the log marginal, cancel the marginals, expand the marginal into an integral over x, and take the gradient into the integral. Now from here, we rewrite this gradient in terms of the score, take out the inner integral, moving the scalars out of the dot product. Now we realize we can write this integral as an expectation over the joint distribution of x and x tilde. And now comes the clinch. If we take our denoising score matching loss and expand the square difference, we can cancel this term, and we realize that a score matching and denoising score matching losses are exactly the same up to a constant. So there we go. So in short, by learning to denoise individual samples taken from p star, we are in fact learning to predict the score of the marginal density of x tilde, which is p star sigma. This is great because for Gaussian perturbation, we actually have an explicit form for the conditional score, so it's very easy to train our model by just drawing samples from our dataset and applying the random perturbations. Now, this goes a long way towards our generative modeling goal, but we're not quite there yet, because the score of the perturbed marginal is not equal to the score of the unperturbed data distribution. To make them indistinguishable from one another, we can just use some very, very low sigma. So in other words, p star sigma now is high fidelity to p star because the perturbation is very weak. However, with low sigma, we can expect to end up with a lot of low density regions interspersed between the data modes, so we have low coverage of the data space. In these regions, our score prediction is likely to be inaccurate, and in order to avoid them, we'd have to know the distribution of data points in the first place, which kind of defeats the purpose of generative modeling. Now, if sigma is high, we suffer the opposite problem. The coverage is now good because our noise fills out a lot of those low density regions. However, we're now estimating the score of a highly distorted version of p star, so it's less useful if we actually want to find the data distribution. So is there a way we can combine the benefits of both? The answer, of course, is yes. But to properly understand it, we must first address the second basic element of our method, which is sampling. To sample from the density using our score function, we use a method called Langevin sampling. Langevin sampling is part of a class of methods called Markov chain Monte Carlo. Put simply, what these methods do is construct a Markov chain whose elements converge to some target distribution p of x. Langevin sampling achieves this using a stochastic process of this specific form with alpha as our step size. So, as we run this stochastic process, our system will visit low-density regions only rarely, and will spend a lot of time in high-density regions. But to see exactly why this works, we'll have to take a brief detour into physics land. Generally, the mass times acceleration of a particle is equal to the external force acting on it minus the force produced as a result of viscous drag with friction coefficient mu. Now, this external force could be deterministic, but it could also be stochastic. In this case, F is composed of a stochastic component and a deterministic component, which is the negative gradient of the potential energy V. What we have now is the general Langevin equation. Now we're going to make three simplifying assumptions. First of all, we're going to assume that the viscous drag is strong enough to push the average acceleration to zero, and this is called the overdamped regime. The second assumption is that our noise term g is equal to the noise amplitude omega multiplied by eta, which we define as the time derivative of the Wiener process W. Now, the Wiener process is a kind of continuous Gaussian process, so it's a continuous stochastic process with Gaussian increments. So you can think of eta as just something which is continuously injecting noise into our dynamics. Now, the third simplifying assumption is that we just set mu to 1, so we end up with this equation. Now, stochastic processes like these generally define a probability density of x that evolves with time, and that time evolution is governed by what's called the Fokker-Planck equation, which looks like this when placed in our context. The expression inside the square brackets is the negative of the probability current J. So positive divergence at a point means that probability at that point increases with time. Now, in the context of Langevin sampling, we're interested in finding what are called steady states, represented by p infinity. Put simply, these are probability densities that do not evolve and just remain constant over time under our stochastic process. And since they are stable over time, we can sample from them. This means that the net influx of probability at every location is 0. Now, it turns out that for our Langevin process, a steady state implies that the actual probability current itself is 0. So there isn't any probability mass being moved anywhere. This property is called detailed balance, and it applies for Langevin steady states with the additional assumption that as x goes to infinity, the probability flux goes to 0. Now, by manipulating this a bit, we get an expression with the score of p infinity. And now we can plug this into our Langevin equation to get this, which we can recognize as a continuous version of our update rule from before. So we've derived our sampling rule by taking an overdamped Langevin process and finding steady states. Now, the wonderful thing about these steady states is that if we run our Langevin process long enough, then the system will eventually converge to our target distribution and stay there. This is true regardless of the initial state. Though, of course, if we drop our particle in some low-density region at the beginning, it'll take some time before our Markov chain actually converges to the target distribution. And this is called the mixing time, or relaxation time. Now, a close look at our sampling rule gives us an intuitive sense of how it works. So here we have a mode-seeking term that climbs the log gradient to find the highest density regions. But of course, our sampler also needs to reach low-density regions on occasion, albeit with less frequency. So we also have an exploration term that encourages us to sample the distribution in its entirety. The coefficients serve to balance these terms, and if they were out of balance, then we would either diverge from the distribution with too much noise, or cling to the modes with too little noise. Now, the catch with Langevin sampling is that it only works if the score is known across the entire space traversed by our particle. So, for example, if we use a score network, then we can't drop the particle too far from our data modes, or else the score network itself will be inaccurate, and our Langevin sampling becomes invalid. Hence, we recover the same issue as before. If we want to do Langevin sampling with low sigma, then we need to know where the modes are, but this would defeat the purpose of generative modeling in the first place. Good news is, we're now in a position to deal with this very issue. The trick is to combine the benefits of multiple noise levels. So we begin by choosing some schedule for sigma between sigma big L and sigma 1. Sigma big L should be low, ideally so low as to make P star sigma big L indistinguishable from P star. On the other hand, sigma 1 should be so large as to make the perturbations fill out all the low-density regions in between modes. So something like a geometric series would work quite well. Now, we imagine that we have trained a score model that can accurately predict the score across multiple noise levels, and we're going to call that the noise conditional score network, following the paper that proposed it. And as you can see, this neural network takes in two inputs, x tilde itself and the noise level sigma. Now let's start off by sampling some points from our base distribution. So here, as an example, we have a uniform distribution from A to B. But really, it could be any arbitrary distribution, as long as the samples produced sit comfortably within P star sigma 1. That's to say, we should be able to accurately predict scores at our initial samples. Now imagine that we set our noise level to sigma 1. This means that using Langevin sampling, we should be able to guide our samples to converge to P star sigma 1, so that now they cluster a bit more at the data modes. We can do this because P star sigma 1 overlaps significantly with the base distribution, so we can make accurate score predictions. Now, of course, we need to run a certain number of time steps at sigma 1 to ensure convergence, and this number can just be a hyperparameter. Now, let's switch to sigma 2. Again, because P star sigma 2 overlaps significantly with P star sigma 1, we can get accurate score predictions and run Langevin sampling to converge to P star sigma 2. So this step is predicated on sigma 2 being close enough to sigma 1. And of course, we can repeat this for sigma 3, and if we wanted to some arbitrarily small sigma such that our samples adhere incredibly closely to the data distribution. Now this is a technique called annealed Langevin dynamics, because we're gradually annealing sigma until it's very small. Of course, if we try to jump too far between sigma values, then we risk getting inaccurate score predictions for some of our samples. So in that way, we have to attenuate sigma rather gradually. And of course, this may require having a sufficient number of noise levels. So this is how our score-based generative model works. We train a neural network to predict the score across various noise levels, then run annealed Langevin dynamics to gradually converge our samples to the data distribution. On a practical level, we define our total loss as a weighted average of score matching losses across noise levels, with each level weighted by some positive function lambda. Let's now look at our sampling algorithm. So aside from our noise schedule, we have to decide two other hyperparameters, epsilon, which is our initial step size for Langevin dynamics, and big T, which is the number of time steps we run at each noise level to ensure convergence. Now the next thing we do is sample x tilde 0 from our base distribution, where 0 represents the time step. From here, we begin our outer loop, and this just loops over noise levels from sigma 1 to sigma big L. So now we define a step size alpha for each noise level. Notice that at higher noise levels, our step size is larger, and that's because our score vectors will tend to be smaller in magnitude. Now the next thing we do is begin our inner loop over time steps. And here we just run sampling steps from 1 to big T. And we just repeat this over noise levels to get our final sample. And that's basically it for our method. That's how we can use score matching for generative modeling. But of course, this isn't the only generative model that uses score matching, and it's interesting to see how our current method compares to the DDPM, even if they were derived from completely different directions. Now, it perhaps shouldn't surprise us that there's a deep connection between score matching and diffusion models. After all, they are essentially both trained on a denoising task, similarly to the denoising autoencoder. In fact, with the X0 parameterization of the DDPM, we explicitly train a neural network to reconstruct the clean image, just as a denoising autoencoder does. Seen this way, a DDPM is in fact just a series of denoising autoencoders, each removing a bit of noise at each time step. But let's try to verify this intuition mathematically. To start off, recall our expression for xt in terms of x0 in the DDPM forward process. This is analogous to our sigma perturbation, except the Gaussian parameters are a bit different. So in the second one, we do not scale our original data point, and therefore the perturbation is not variance preserving. Now, if we take the score of our xt conditional and separate the terms, we can strike this first term because it has no dependence on xt, and take the gradient to get this. And of course, this looks a lot like the score of our perturbed conditional, and this is no surprise since they're both Gaussian. Now from here, we can summon our expression for xt and rearrange before plugging into our score. So what this tells us is that predicting the score and predicting the noise are two sides of the same coin, since they are equal up to a constant. The noise and score point in opposite directions, which makes complete sense since by climbing the log gradient, we are undoing a noise perturbation. So we can imagine that instead of a noise prediction network, we instead have a score prediction network, and we can use this to indirectly compute the predicted noise epsilon hat. In this case, we would use a score matching objective, which is equivalent to the noise matching that we had before. So in a deeper sense, the DDPM and noise conditional score network are being trained with the same objective. However, one big difference lies in exactly how they sample. As you can see in the DDPM, there is no inner loop, so it progresses through noise levels very quickly. On the contrary, in the NCSN paper, they use at least 100 time steps per noise level. However, for the NCSN, they only use 10 noise levels, compared to 1,000 for the DDPM. So at these settings, both actually use the same number of forward passes. And this is a common drawback of both methods. They are both very slow at sampling. And of course, in future videos, we'll explore how we can deal with that. But for now, that's it. In this video, we've seen how score matching can be used to overcome or circumvent the normalization problem in generative modeling. Then we drew a connection between score matching and denoising autoencoders, and saw how we can use annealed Langevin dynamics to generate samples from a target distribution. And finally, we drew an explicit connection between score matching and diffusion models, showing that noise prediction is equivalent to score prediction. In the next couple of videos, we're going to see how the DDPM and NCSN are in fact two special cases of reverse time diffusion, and we'll see how we can migrate our methods to the continuous regime for more generality.